Okay. Hi everyone. Hi. So, by the way, I believe today is important. I don't know why too many people came, too few people came, but today is important. We are going to talk about boosting, which is very important, but that's fine. So, last time we ended up in random forest, but we couldn't finish it. So let's finish random forest. So, we said that for random forest, we need to explain bagging, which is short for bootstrap aggregating, and it's not related to bag at all. And then we said it's a meta algorithm, which can be used with other machine learning models, such as classifier, regressor, etc. And then we defined bootstrapping, which is basically simple random sampling with replacement. They call it bootstrapping in statistics. Then we said in bootstrap aggregating, it says bootstrap from your data and train a model with this bootstrap sample, then do it again, train another model. So you will have several models trained by different data. And then in the test phase, you aggregate them. So in the test phase, when a data comes, you feed it to the models, you will get several results, right? Several predictions. But what is the final prediction? We need to aggregate the predictions of the models to get the final prediction. How can we aggregate them? Such as average. We can get the average, right? So that's why also it's called model averaging in statistics. These are the terminologies that are used in the literature. Also, as we are using several models, they're also called ensemble learning. So it's an ensemble. So we showed that in these two slides, we explained that in the previous session that when the models are very similar to each other, then it's basically like using only one model. It's nothing much different. But when we have when the models are very different, uncorrelated, then the variance of estimation is divided by the number of models. So as a result, it's good to have different models, right? So we said that random forest, one of the examples of the bagging in machine learning is random forest, proposed in 2002. And what does it do? In random forest, we train different models. Models are trees here, using different bootstrap samples, which are subsets of training data set, right? So random forest is a bagging method, but as we want the trees to be very different, in addition to being different in terms of bootstrap samples, we also sample from the features, okay? In addition to sampling from the data points, we also sample from features. So every tree will be trained by different features also. Why do we do that? Because we want the trees to be very different, right? So this is random forest, and as I said, we also sample from the features or dimensions of the bootstrap sample. And we have, by the way, various types of random forest. So random forest, extremely random forest. But anyways, all of them are like such as an ensemble of trees, but with different some variants. I think the theory is important, but the variants, you can go and see what they are. One of them, for example, one of the variants is extremely random forest. Another one is so, for example, random forest has been proposed for anomaly detection, and that's called isolation forest. So let me write them down for you. Extremely random forest, or random forest itself, random forest, original random forest, right? Or isolation forest is for anomaly detection. Anomaly detection is another name. Anomaly detection is another name for outlier detection. Okay, when I say a point is anomalous, it means that the point is outlier. And by the way, do you know what is it doing? Let me tell you briefly what isolation forest is doing. Assume I have a cloud of data points and I have an outlier. Okay. So you apply some tree on it, consider a tree, and you want to partition the space. What will your tree usually do? Can you tell me? Will it split the space from here or probably from here? This one is, it seems that the tree will split. So as a result, it has captured the outlier, but this goes further, right? In the tree, we go further in the depth. So it go. But which one do we know that which partition is the outlier partition? The partition which happens sooner in the tree. As I said, because these partitions happen sooner, and then we go further, and we partition the space further, right? The inliers, which are not outliers, they usually come at the end of the tree. The outliers appear sooner in the tree. As a result, the depth of the tree, the depth of the point in the tree, or the depth of the partition in the tree, the depth of the child in the tree determines how outlier it is. The less the depth, the more anomalous it is. Okay, interesting. So that's the main idea behind isolation forest. And I think it's named because it isolates, right, the anomalous points. So another one is Mondrian forest. I'm just enumerating their names for you. If you are interested, you can look them up. Mondrian forest is for online data. So you wanna, do you know what online data means? The streaming data. The data is coming, right? It never ends. So its opposite is, they either call it offline data or batch data. Batch data is also means offline data. It's not a streaming. But when the data is coming, right, it's coming. It's online. By the way, online data can be time series. It also can be not time series. What do I mean? For example, you have some cloud of data points, right? More data are coming in the cloud, so it becomes more occupied, more busy cloud, right? This data is not time series, but it is online. Okay, and online data might or might not be time series. But when it is time series, it's definitely online, right? It's coming. Unless you have a batch of time series, but and it never goes further. I think that's useless in machine learning. We usually train with a time series because it goes further and further, right? Such as a stock, such as weather. We have future. If we don't have future, what's the point of having time series? Yeah, Mondrian forest is for online classification or online regression using forests or trees. By the way, when we say forest, you can see it as an ensemble of trees, right? For example, for isolation forest, I talked about isolation tree, but when we have an ensemble of them, it becomes isolation forest, right? Basically, we have a score of isolation by every tree, and then we have the model averaging of the scores of the outlier in isolation forest. So Mondrian forest I talked about, isolation forest I talked about, we have a hybrid of them too. It's called isolation Mondrian forest. Or Mondrian forest. Do you know whose paper it is? Our paper. Let me show you. Isolation Mondrian forest. So isolation Mondrian forest for batch and online anomaly detection. Can you guess what it is doing? Do you remember what I said? Isolation forest is for anomaly detection, but offline anomaly detection, or batch anomaly detection. Mondrian forest is for online classification or regression. Their hybrid as Iman rainforest is for online anomaly detection. So basically, you have, for example, this cloud of points, and the points are coming, right? Some of the points which are coming become outlier, right? These are outlier, but the being outlier also depends on the time. So what do I mean? For example, in this time stamp here, this is let me erase some of them. In this time stamp, this is an outlier, right? This one, agreed? So the Iman rainforest in this time, you say this is an outlier, but more points are coming, and this becomes like this, and this is not an outlier anymore. So it changes. The status of being outlier changes during the time. That's interesting, right? Okay. So yeah, we have a lot of various types of forests. Acknowledgement. Here I already said that. Oh, there are variations of decision tree, but they all have the same base that we discussed. Some variants of the trees are also famous, but they have the same background that I talked about. So one of them is C4.55. They used to name them in weird names, such as this C4. They coded the names C4.55. I think maybe that's the version C1, C2, something like that. So it was proposed in 1993. Another one was CART, proposed in 1984. As you see, they are old, and these are trees, right? For more information on CART, you can see reference 10. For more information on decision trees, you can see these references. For more information on trees and machine learning, you can see this book of Hasty and Tipshurani, The Elements of Statistical Learning, Data Mining, Inference, and Prediction. You know Hasty and Tipshurani, right? They are in Stanford University. This book talks about trees well. And some slides of this slide deck are also inspired by teachings of Professor Ali Qudsi at the University of Waterloo and also Professor Huda Mohamadzadeh at Sharif University. Okay. And these are the references. By the way, the memory is coming. The history is coming in my memory. I remember in my end of bachelor or start of master's, I also proposed tree-based optimization. So I said, why not using tree for meta-heuristic optimization? So meta-heuristic optimization is a search, okay? And so we search in the space. Then I said, let's partition the space and search in the partitions. And then in this way, we reduce the search space. And that was called, if you want to see, it was, yes, good times. Tree-based optimization, a meta algorithm for meta-heuristic optimization. It was one of the very first papers of mine, I remember. Okay, so if you want to see how it works like this. Let me show you. So for example, it partitions the space one by one. What? So it's not theoretical, actually. My first papers were not that much theoretical. But because meta-heuristic optimization is not that much theoretical, and it's easier to publish in those areas. That's why I started with those, because I wanted to publish. Yeah. Have you seen my very first paper? Let me show you so you laugh a bit. I think, yeah, it was a good paper, and my professor is a very wonderful professor. He used to be my supervisor in undergrad. He was very knowledgeable. But I'm saying that the reason I said laughing because it doesn't have much mathematics and it has a lot of figures. I remember. So what is this? This is Gamaros, a creature in the Caspian Sea. So because there are a lot of nature-inspired meta-heuristic optimization. And And with the help of my professor, we proposed this algorithm for search in the space. And I said laughing because of this figure. I even put a cartoon in my paper to explain the algorithm. I remember it took me a long time to draw this in my computer. Anyway, but yeah, it's good to acknowledge my professor, Said Sharifian, a very wonderful professor in my undergrad. Okay, so let's continue. I think it's time to talk about, yes, it's time to talk about boosting, which is a very serious lecture. And you need to focus. It has a lot of math, okay? Assignment. Yeah, okay, sure. In MLE, we assume that covariance matches are equal. Yeah. But it you use two different covariance matches. Why we should use that? So the question is, in LDA, we are saying that LDA assumes that assumes equivalent covariance matrices for the classes, right? So, but do remember that, let me bring the LDA lecture. Where was that? I said, how do we then find because the classes obviously have different covariances, probably. It's very rare that the two classes have the same covariance matrices. Then I said, how do we find the shared covariance matrix in LDA? I think it was here. Let me find it. Yeah, in equation 36. In LDA, we assume that the covariance matrices are equal. Therefore, we use the weighted average of the estimated covariance matrices as the common covariance matrix in LDA. Right? Where NK is the cardinality of the class K, and N is the cardinality of total data. Did you understand? Any other question about assignment? About yes? No? Yeah, it's. I said that. Where did I say? Until where? I think I said. Did I say logistic? Did I say? Until the end of?
After that, you said before boosting, not included boosting, not included.
So, but you said I said until the end of logistic regression. Did I? If let me see what I said. I don't exactly. So I said will be until the end of logistic regression. Before, okay, so until the end of the logistic regression. So trees will not be in the. No. So whatever I said here, trees will not be in the exam. Okay, until the logistic regression, until the end of logistic regression. In other words, so whatever we taught until the end of logistic regression. Okay. What? For deep learning, I said it in the deep learning. Whatever I said for the in the announcement of deep learning, I don't remember, but that was, yeah. So, but yeah, when I say until something, it means that in the order that I taught until that. Okay. So yeah, as I taught 3 after logistic regression, it will not be in the exam. Okay. So any other question? Everything was clear? What? Yeah, it was my mistake. Sorry. Because I think last semester it was including forest. I copied pasted and I forgot to edit that part. Sorry about that. Yeah, okay. So let's talk about boosting now. Okay. Please focus and follow what I'm saying. It's a very cool lecture, I believe. So definition. Boosting is a meta algorithm. What do I mean by meta algorithm? I already said that. So it can be used with other algorithms, right? Which can be used with any model, any classifier, regression, etc. For binary classification, for example, if we use boosting with classifier, even slightly better than a flip in a coin, we will have a strong classifier. So assume I'm using boosting with binary classifier. Can you tell me that if I train a binary classifier and its accuracy becomes 49%, is it a good classifier or not? No. Why?
Algorithm has not.
Yeah, but what? Yeah, exactly. Because assume I get a coin and I randomly flip it, and every time, for example, it's head, I say class 1, otherwise it's class 0 or something like that. Its accuracy will be 50% if I do it a lot. If the number of trials goes to infinity, the accuracy becomes 50%. So it means that even it's worse than random guessing. It's random guessing, right? It's even worse than random guessing. So if, for example, I have 3 classes, my accuracy must be what? Above 33%. So if you have 3 classes in industry and you get 30%, don't go to your manager. They will shout at you, right? Because it means that it is awful if it is less than 33%. So basically, yeah, as I said, but interestingly, if it is 51%, it's still an awful classifier for binary classification, but it's better than random guess, right? Even 51. Interestingly, if you use several classifiers with accuracy 51, even slightly better than flipping a coin, and we use them with boosting, it works very well. The accuracy becomes maybe 80, 90%. Okay, interesting. And we will see why. We will see theoretically why this happens. Thus, we can say boosting makes the estimation or classification very strong. Hence the name boosting. It boosts them, right? In other words, boosting addresses the question whether a strong classifier can be obtained from a set of weak classifiers. Okay. The idea of boosting is to learn K models. By the way, boosting can be seen as an ensemble learning tool, I believe. Okay. In my opinion. So the idea of boosting is to learn K models in a hierarchy where every model gives more attention or larger weight to the instances misclassified or estimated very badly by the previous model. Did you get it? So basically, I have a hierarchy like this, shown in this figure. So H1 to HK. So I give all of the data points to H1. So it performs well on some of them, right? And worse on some other points, right? For the points where H1 didn't perform well, I weight them more for H2. So H2 should consider them with more weight, should attend to them more, right? And so on. So H2, see which ones work better on H2, etc. And then we weight them again. So finally, the overall estimation. So by the way, from each of them, we have some estimation, predicted value, right? But what is the final one? Again, we need to aggregate them, right? So aggregation is a linear combination of them with weighted linear combination with weights W, alpha J, alpha 1, alpha 2 until alpha K, right? So alpha 1 H1 plus alpha 2 H2 until alpha K HK, right? We add them, it gives us F hat of X, which is the estimated, final estimated one. If the model is classifier, then we can use sign. So we aggregate them and then we use sign to become either +1 or -1 for classification, for example. Or we can do majority voting, right? Okay. Different methods. Boosting is a family of methods, right? It's a family. The most famous one is AdaBoost, also pronounced as AdaBoost. AdaBoost. It's short for adaptive boosting. Okay. It was proposed in 1996. The algorithm of AdaBoost for binary classification is shown in this algorithm. So what is it doing? We'll see. So we'll talk about every step of this. In this algorithm, okay, LJ is the cost function minimized in the jth model HJ, because we know everything in machine learning is optimization, right? HJ needs to minimize some cost function. Let the cost function or loss function of the model HJ be denoted by LJ. Okay. I is the indicator function, which is 1 if its condition is satisfied, otherwise it's 0. Okay. Okay. I is used here. LJ is here, also here, right? WI, which is here, also here, is the weight associated to the ith instance for weighting it as the input to the next layer of boosting. Do you remember I said we weight the data points, the data instances? If one model works poorly on some data points, we should weight them more for the next model, right? And WI is the weight for the ith instance, ith data point. So I goes from 1 to n. N is the number of data points, okay? Yeah. I is the number of data points. Indicator function, so assume, I want to say whether it's raining or not, okay? Indicator function of it is raining. It is 1 if it is raining. Otherwise, it's 0. So basically, there is some condition here, and this condition might change, right? So it is raining. It might rain actually. Then it becomes 1. If it is not raining, then it becomes 0. So indicator function has some condition in it. And if the condition is satisfied, it gives me 1. This is indicator function, which we usually use in machine learning. Indicator function in optimization, I told you, it's slightly different. Do you remember? For interior point algorithm, I said if its condition is satisfied in optimization, it becomes 0. Because plus 0 doesn't do anything in the cost. But if its condition is not satisfied, it becomes infinite to blow up the cost function. That was for optimization. Here we are using it for machine learning. Okay. Yeah, indicator function. Yeah, exactly. So here, basically, it checks whether yi is the actual label of the data point, ith data point. HJXI is the predicted value of the predicted label for xi in the model J. Okay. Are they equal or not? So note that the cost in AdaBoost is this. So LJ, do you remember the cost of the jth model is this? And we'll talk about everything. By the way, what is it doing? So basically, it's summing up. Does it make sense? Does this last make sense? We know that when we say loss or cost, we want to minimize it. So it must be bad. Must be bad. So what is this indicator function saying? That our prediction is wrong by the jth model, right? And we are summing, and this is for the jth model, right? And we are summing over the points, data points. So for the jth model, it's basically counting how many wrong answers I have. But I'm weighting them as well, WI. So the points are being weighted, right? So if I don't have WI, the summation of indicator function basically counts how many points are being misclassified or wrongly predicted by the jth model. But now I'm weighting them. And also in the denominator, I have the summation of over all of the weights, because I want them to be, I want LJ to become between 0 and 1, right? Okay. Basically, it's like, as it is between 0 and 1, you can see it as the probability of error for the jth model, right? And we want to decrease it, minimize it. Okay. So here we can have several cases which help us understand the interpretation of the AdaBoost algorithm. Let's see. If an instance is correctly classified, then this indicator function is 0. Why? Because yi will be equal to hjxi. Thus, wi will be still wi without any change. I'm talking about this line of the algorithm. I'm interpreting this line. So when it's correctly classified, this becomes 0, right? What is e to the power of 0? 1. Then wi becomes wi. So basically, its weight will not be changed, right? Because it's correctly classified. Yes. However, if an instance is misclassified, this becomes 1, right? Then wi becomes wi times e to the power of alpha j. So basically, we change the weight. This is exactly what I started with. I said, if a point is misclassified, I need to weight it for the next model. When I say weight it, I mean change the weight. Because initially, all of the weights are equal to each other. And they are 1 over n. Why? Why do I initialize them by 1 over n? Because I want them to sum to 1, the weights to sum to 1 with the equal weights, okay? Then, gradually, I modify the weights when I go down in the hierarchy, okay? So this for loop is going down in the hierarchy, right? It's the loop over the models. Okay, now when this happens, when this misclassified, right? 2 sub-cases might happen. So if the classifier which classified that instance was a bad classifier, the hj was a bad classifier, its cost would be like flipping a coin, right? Let's say lj will be half. It's considered a binary classifier. LJ will be like flipping a coin. It's a bad classifier, right? Therefore, what happens? Can you tell me? Consider this line of the algorithm. Alpha j is logarithm of 1 minus lj over lj, right? When hj is a bad classifier, lj is close to half, or half, doesn't matter. Then what happens in the logarithm? 1 minus half becomes half over half. Half over half is 1. So the fraction inside the logarithm becomes 1. What is logarithm of 1? 0. So alpha j becomes 0. Then this alpha j also appears in the exponential operator, right? So wi becomes wi e to the power of 0 times 1, which is e to the power of 0 is 1. So wi doesn't change, right? But what if we misclassified the point by a good classifier? Then we can trust this misclassification, right? In this case, this alpha will not become 0 anymore, right? Because lj will not be half, will be much higher than half. For example, if it will be 0.7, then the fraction inside the logarithm will be 1 minus 0.7, which will be 0.3 over 0.7, 3 over 7, right? Logarithm of 3 over 7. Then the wi in this equation will be wi times e to the power of alpha j, right? And it actually increases because I believe e to the power of alpha j will be greater than 1 for this. You don't believe me? Let's analyze it. Let's analyze it. We know that lj is greater than half. What happens to 1 minus lj over lj? It becomes less than 1, right? Am I right? E to the. Yes. Yes. So alpha j is here, right? Between 0 and 1. Agreed? Do you agree that this part is greater than 1? Because e to the e to the power 0 is 1. Agreed? So e to the power of alpha j is greater than 1. As a result, wi gets larger. Right? I'm changing the weight in a way that I increase the weight of the misclassified point. Okay? Let me summarize these 2 points. It's very important. Let's summarize from scratch. I have a point. Consider everything. This point is now I'm in the jth model in the hierarchy. Okay. This data instance is either classified correctly by hj or misclassified by hj. If it is correctly classified by hj, don't change its weight because it's already classified correctly. However, if it is misclassified by hj, now should I trust this misclassification or not? Should I be pessimistic? Probably the hj incorrectly misclassified the point. Did you get it? Incorrectly misclassification is equivalent to kind of correctly classification. Or at least I can say I can't trust it. Because what if the model is noisy? Okay, so then it is misclassified. I should check whether should I trust this model or not. If the model is a bad model, I don't trust this misclassification and I still don't change the weight of that point. But what if it is misclassified and the model is trustworthy? In this case, I increase the weight of this data point for the next model in the hierarchy. Did you get it? Interesting. So this algorithm is completely explained. We initialize all of the weights of all of the points by 1 over n. Then we go in the hierarchy by the for loop, every model in the line 3 of the algorithm. Every model minimizes Lj, where Lj was defined in this slide. We talked about it, equation 3, right? It's a kind of probability of error of the jth model. We want to decrease it. So basically in line 3, we train the model hj, right? It's argument of Lj, so minimize Lj, we train it. It gives us the trained hj model. Then we check how this model performs on the data points, right? We evaluate the model. In line 4 and 5, we are evaluating the model. So in this indicator function is kind of evaluating the model for the ith point. Then a combination of line 4 and 5 is the analysis that I told you. Whether we change the weights or not. In line 5, we are updating the weights for the next model. Then after this update, we go to the next model in the for loop. Agree? Interesting. So far, we just described the AdaBoost. Now, the theory behind it. Let's go inside them, okay? So, additive models in science, additive models can be used to explain why boosting works. It's in statistics, additive models. In an additive model, by the way, I think in my deep learning course, I talked about additive model for radial basis function, I believe. But here, I'll also explain that. In an additive model, we map the data X. So consider phi j is a map, okay? By the way, you know what map is in mathematics, right? Map function is a special case of map where I don't have 2 different outputs for the same input, okay? Map does not have such restriction. It's just a map. Phi j gets x and maps it to phi j x, and the map is denoted by this in mathematics, by this notation. For all j, so I have k models. For all j from 1 to k, I have k maps, and then add them using some weights, beta j. So basically, I have some data. I map it k times with different maps, right? Then I will have k transformations of this data. I aggregate them by weighted linear combination, right? With the weights beta j. Agree? Okay. This is called additive model in statistics. A well-known example of this additive model is radial basis function neural network with k hidden nodes using Gaussian mappings. I already talked about it in my deep learning course. Now, the boosting can also be explained by additive model. Let's see. Now consider a cost function for an instance, data instance, as this. Consider L, Y, and H. So the cost or loss function gets Y and H of X as inputs. So H of X is a predicted label and Y is the actual label. Okay. What does it do? It's defined as e to the power of minus Y Hx. Does it make sense? Assume my actual labels are +1, -1. Okay. Binary classification. Does it make sense? Let's see. What if Y is 1? H of X is also 1. Then I will have e to the power of -1, right? Which is a small value. So we know that when Y is 1, H of X is 1, it means that it's correctly classified. So the loss must be small. E to the power of -1. Agree. What if Y is -1 and H of X is also -1? It's still correctly classified. And it becomes e to the power of -1 and the loss is small. But if the signs of Y and H of X are different, one of them is 1, one of them is -1, then it becomes e to the power of 1. The loss becomes large. So this loss function makes sense, which we want to minimize it because it gets large for misclassification, right? Now, I assume we add up the costs over n training data instances. So this was for 1 training point. Now I assume I have n training points. So I will have yi and h of xi, and I add them in the summation. LT denotes the total cost. Okay. Okay. T stands for total. Now, in equation 4, where was the equation 4, which is here? Phi of x is this, right? This is what we had in additive model. If we rename the mapping to h of x, assume my mapping is the model h of x, okay? Do you remember? Recall preliminaries. I said machine learning model is like a map. Okay. H of x. Then the additive model becomes this. H of x is summation of beta j hjx. Where did we see that? This is exactly the aggregation in the AdaBoost, right? In the boosting. We saw that. We can write this expression, equation 7, as a forward stage-wise additive model. Let's see what it means. In which we work with the models one by one, where we add up the previous worked models. So we start with one model, then we work on, then we go to the next model, then we add the first and second model. Then we go to the third model, then we add the first, second, and third model, etc. Right? In this case, so we can write it in this case, like this. F of fq x is fq minus 1x plus beta q hq. This summation can be written as this, right? Where fq minus 1x is this summation where j goes from 1 to q minus 1. So these two together are equivalent to equation 7, right? And k goes, q is less than or equal to k, goes to k until k. Q is an integer, by the way. Okay. H, and finally, the last one is fk, right? When q becomes k. hx becomes fk, which is this hx, right? Because hx is all of the summation for j from 1 to all of k. Agreed? Did you get it? Okay. Now, therefore, minimizing the cost, which was equation 6. This is equation 6. I'm repeating it here. Okay. This was the cost. Do you remember the total loss? For the jth model, is an additive in an additive manner. Is this in the additive manner? So let's see. What am I doing? So rather than hxi, I I wrote it as this additive model which we discussed, right? So it becomes Fj minus 1 xi plus beta j hj xi. And F is defined like this in equation 8. Agreed? Please focus, because if you miss one step, you might get lost. Okay? They are related to each other. So this part is written as this part. Then, can you tell me what am I doing? We know that e to the power of a plus b becomes e to the power of a times e to the power of b. So I have this term times this and also this term. So I separate them as a multiplication of exponential operators, right? By the way, here my optimization variable becomes beta j and hj, right? Beta j is here and hj. So the models and also their weights. So this is what we had. I'm repeating it. Now the first term, which is here, the first term here, is a constant with respect to beta j and hj. So it's constant with respect to optimization variables, both of them. So I can drop it, right? No, here apparently I didn't drop it because I think arg min is also important to me. No, I can't drop it. Sorry. It's not added. If it was, for example, a plus b, and a was constant with respect to the optimization variables, I could drop it, right? It's a b here. Okay, so sorry about my mistake. We can't drop it, but we can name it because we can see it as a capsule, right? As one thing. So I name it to be wi. I name the whole thing here to be wi. So this cost function becomes this, right? This optimism. Agreed? Okay. Now, as in binary AdaBoost, we have +1, -1. We know that for the labels and for the predictions, we have +1, -1. Agreed? So basically, what can we say? Let me think what we have done. Okay. So consider yi and hjxi. They are either +1, -1, right? Either they are equal to each other, so they are both 1 or both -1. In this case, I will have e to the power of minus beta j. Agreed? Because yi times hjxi will be 1 if they are the same, right? So I will have e to the power of minus beta j, and it's not related to I, so I can bring it out of the summation here. And then also yi is here. Agreed? Indicator, I'm using indicator function here again. Then the other case, yi and hjxi might have different signs, right? Agreed? Do you follow me, by the way? Yes. So in this case, I will have e to the power of minus beta j minus. So I will have e to the power of beta j, and it is not related to I, which comes out of the summation. Agreed? So I wrote this as two summations using indicator function. Then consider this summation. Summation of yi, indicator function of yi, wi, indicator function of yi equals hjxi here. Do you agree that I can write it as a summation of all of wi's minus summation of wi, indicator function yi is not equal to hj? Basically, this plus this is the whole cases, right? Agreed? The whole cases. So this is the whole case. The whole case minus one of the cases becomes the other case. This is exactly what we have done. Right? Right. So as a result, I replace this summation by what I just explained. So I will have these two terms. The first term is broken down into these two terms. The third term is repeated. The third term is repeated. Right? Clear? Bear with me and you will see the beauty. You need to bear with me. Okay. Now I have this. So we found this. I'm repeating it. What should we do? Minimization of a cost function without any constraint. What should we do? What did take derivative, set it to 0, right? As in high school. Okay. According to the first order optimality condition. Take derivative. The derivative now, consider one of the optimization variables, beta j for now. Derivative of this LT with respect to beta j. What happens? Okay. So this is constant multiplier. So it's here. What is derivative of e to the power of minus beta j with respect to beta j? Because becomes minus e to the power of minus beta j. Agreed? Here it is. So what about this? This is also minus e to the power of, it becomes, its derivative becomes minus e to the power of minus beta j, but I have one minus here, they cancel each other, it becomes plus. This, and this is also constant multiplier with respect to beta j. Its derivative is the same as itself, and this is repeated here, right? Set it to 0. And we know that this is scalar 0 because the beta j is a scalar. Then what happens? Let me think. What have we done here? Okay. Let me clear this part so you can see it better. Do you agree? Consider these two terms, this one and this one. The only difference of them is this, right? These are the same. Factor out this same part, right? Factor out this same part, which is here. You will have these two terms. Agreed? Also, this part, bring it to the other side of the equation. Then multiply the sides or divide the sides by this summation. Did you get it? So basically, this first term is this times this. Okay? Then, interestingly, let me clear this part. This is exactly what we had defined as LJ. This is our LJ that we had, right? So I'm replacing it with LJ. Right? Agreed? Now, rearrange the parts. So this can be divide the sides by this. LJ becomes this. Okay? So far clear? Now, so solve this equation for beta j. Okay, if you do that, if you write it down, so it needs some calculations. You will get this. Because this expression is expression based on beta j for LJ. Do it the other way around. Make it expression of LJ for beta j. Okay, you will get this. Okay. Now I have exp operator, exponential operator. It's a pain in the neck. What is its opposite operator? Logarithm. So take logarithm from the sides. Then you will have 2 beta j equals log of this, right? Log of the right-hand side. Okay. What was this? Do you remember? The right-hand side. Recall the algorithm. Let's go back and see the algorithm. This is according to line 4. It's alpha j. Did you see that? Let's go back to where we were. As a result, alpha j equals 2 beta j. Yes? So far clear? I know it's a bit lengthy, the proof, but at the end it blooms. Okay, let's listen. So consider equations 8, 9, and 10 that we had. I'm repeating them here. Okay. So, and according to these three, we have equation 12. Let's see why. Let's see why. Because of this. What is f? This here we have fj minus 1 xi, right? And for fj minus 1 xi, according to this, I can replace it by beta j hj xi. Okay. Now, so this is y wi. Now, interestingly, I have yi here and hjxi here, right? Do you agree that they are either their multiplication is +1 or -1 because they are either 1 or -1? It's for binary classification. As a result, as I can write minus yi hjxi as 2 times indicator function of yi minus is not equal to hj minus 1. Let's see, let's analyze it. If yi and hj are not equal to each other, it's misclassified, right? This indicator function is 1, right? Then becomes 2 times 1 minus 1 is 1, right? We know that when it is misclassified, this part becomes -1 times -1 becomes 1. So the two, this is for misclassification. Now the proof of this for correctly classification. If yi equals hjxi, this indicator function becomes 0. 2 times 0 minus 1 becomes -1. The left-hand side also, this part is 1. -1 times 1 becomes -1. Right? Interesting. So this is true. Now, as a result, by the way, we know that alpha j, we just proved that here. Here, alpha j is 2 beta j. Agreed? We just proved that. So I think I need to write it down for you to understand. Put equation 13 in equation 12. What happens? It becomes beta j. It is a bit lengthy. I need to have more space. Where do I write it so I have more space? I write it here. Okay. I'm putting equation 13 in equation 12. It becomes beta j, agreed, times 2 indicator function of yi not equal to hjxi, agreed, -1, this, agreed? So now we know that here 2 beta j appeared, which is alpha j. Agreed? By the way, I know that e to the power of a plus b becomes, or a minus b becomes e to the power of a times e to the power of minus b. So basically, this term, first term, is here. This beta j times this -1 is the second term, is here, right? Agreed? And also I had exp of a minus b. I wrote it as exp of a times exp of minus b. Okay? And I replaced 2 beta j with alpha j. Agreed? And because we proved this alpha j equals 2 beta j in the previous slide. What is this? Did you see that before? Equation 14. Did you see that before? Where was that? Consider this. Do you remember this part? That was the formula in the algorithm for updating WI. Let's go back. Line 5 of the algorithm. I just proved it for you, right? But you might be wondering what happened to the last term, which was multiplied. I'll tell you that it's not important. Ignore it. This is equivalent to the formula of WI in the algorithm with a factor, so up to scale, okay? This factor does not have impact on whether an instance is correctly classified or not. Okay, as a result, it's equivalent to that. Doesn't have impact on correct classification. So we proved the formula so far, right? That was a proof of the AdaBoost algorithm. It was a bit lengthy, but we did it. Now, let's go a bit further and talk about why it is working well. Do you remember I told you that if we boost several classifiers which are slightly even better than random classification, the result becomes a monster. Let's see why. So for that, what should we do? We can calculate the probability of error and see how much is it. For that, whenever I have something which is bad and I want to minimize, rather than minimization of that thing, that function, I can minimize its upper bound, right? When I have a function, I want to minimize it, I should either minimize the function, or a good technique is that I find an upper bound on that and I minimize the upper bound. As both upper bound and the function are functions of the same variable, when I find the variable which minimizes the upper bound, that also minimizes the actual function, right? So this is a good technique, and we are going to do the upper bound on the generalization error of boosting. Okay, and we know that generalization error is important to us, which is a true error, right? Okay, there is an upper bound on the generalization error of boosting. In binary boosting, we have +1 and -1 for labels and also for the predictions, right? So YIF, consider maybe F hat might be floats, and then we threshold it. Doesn't matter. The sign is important. Therefore, YIF hat of xi is less than 0 means that if this happens, means that we have error for estimating the ith instance. Let's see why. If yi and f hat xi have different signs, what does it mean? It's misclassification, right? Right? If they have different signs, their multiplication becomes negative. So when yi f hat of xi is less than 0, it's bad. It's misclassification. Agreed? Right? Now, let's take it a bit easy on it. Rather than saying less than 0, let's say less than or equal to some theta, where theta is greater than 0, right? Assume theta might be 0.0001. It's a small positive number, right? Let's relax it to this, equation 15. And that's a bad thing, right? It's misclassification. Recall equation 1 that we had. I'm repeating it here, right? This is the aggregation of the results in the boosting. Now we can normalize this equation because the sign of it is important. When the sign is important, does the value matter? No. So I can normalize it to become equation 16 by summation of alpha j. Okay. Now, according to equations 15 and 16, these two, What do we have? We know that starting from equation 15, which was bad, right? Let's see. I replace f hat of xi with equation 16. So I'll get this. Also, at the same time, I multiply the sides by the denominator of equation 16. Okay. And I know that summation of alpha j is greater than or equal to 0, so it doesn't change the direction of the inequality, right? Then rearrange the terms. So bring this to the right-hand side, and then multiply this. And so bring this to the right-hand side, then the whole thing becomes greater than or equal to 0. Agreed? Agreed so far? Then when something is greater than or equal to 0, take exponential operator from the sides. Take exponential. So exponential operator of this becomes greater than or equal to e to the power of 0, which is 1. Agreed? Okay. So this is what we had. I'm repeating it here. Right? By the way, this means error, right? This means error. Therefore, in terms of probability, so the probability of this equals the probability of this. And this is the probability of error. There are some inequalities which are important in probability, okay? One of the important inequalities is called Markov's inequality. What is that? It has some proof, but we don't go over its proof. We use that here. So for a, which is greater than 0, some scalar a, and the random variable x. By the way, a is not random. It's deterministic, okay? X is random. It's a stochastic, okay? Don't worry about these names. A stochastic means random. Deterministic means not random, okay? Then what happens? This is the formula. A very famous formula. You can use it in your own research as well. Probability of x greater than or equal to some a is positive, is less than or equal to expectation of x divided by a. Okay? This is called Markov's inequality. Now consider equation 17 as well. What happens? Can you tell me? What is equation 17? Consider the right. Let me think. Consider the left-hand side of equation 17. Isn't it similar? No, sorry. I apologize. Consider the right-hand side of equation 17. Isn't it similar to the left-hand side of equation 18? What is left-hand side of equation 18? Probability of x greater than or equal to a. What is the right-hand side of equation 17? Probability of something e to the power of something is greater than or equal to 1. So let a be 1. A equals 1. I'm going to use, so this is the left-hand side of Markov's inequality. It's less than or equal to, according to the Markov's inequality, this. We know that a is 1. So division by 1 is nothing, right? So the numerator is expectation of that thing. And what was that thing? It was this, right? Basically, you can see it as probability of Benjamin greater than a is less than or equal to expectation of Benjamin over a. A is 1, so probability of Benjamin greater than or equal to 1 is less than or equal to expectation of Benjamin. And here Benjamin is expectation e to the power of this whole thing, big thing, right? Agreed? Okay. This is what we had. I'm repeating it. Let's continue it. Do you agree that? So here I have e to the power of a plus b. I write it as e to the power of a times e to the power of b. And I have e to the power of theta summation alpha j. My expectation is over with respect to data or xi. So for my expectation, xi and yi are important, right? And we know xi and yi can be seen as a random variable. So theta summation of alpha j is nothing related to xi and yi, right? So they are not random. We can bring it out of the expectation. Agreed? So I will have expectation of this term. Then this term is random. It stays in the expectation. Expectation of e to the power of minus yi summation alpha j hj, because it has yi, also xi. Agreed? Did you follow? You seem a bit confused, no? Which part is confused? Where did you lose it? Previous, which is, tell me, stop me. I didn't understand this part. Which part didn't you understand? What? Accept it from me as a formula. Okay? It's a formula called Markov's inequality, where x is a random variable. I'm gonna use this. Did you understand equation 17? Now, consider the right-hand side of equation 17. Isn't it similar to the format of the left-hand side of equation 18? So according to this formula, which I'm gonna use, and set A to be 1, probability of x here is the whole thing here, which is big. X is this. Probability of this greater than equal to 1 is less than or equal to expectation of this big thing over 1. It's here. Okay? Any question? Anyone? Everyone? Clear? Now, so this is what we found. Let's continue that. I have expectation of, sorry, e to the power of something plus something. I can write it as e to the power of that one thing times e to the power of the other thing. E to the power of this is not random. I can bring it out of the expectation. And then I have expectation of this, which is random. This inside is random. Okay. To recall preliminaries, I can approximate expectation by mean, by average, right? By average. Expectation is mean, sorry. And another name for expectation is mean. I can approximate mean or expectation by average. This is called Monte Carlo approximation, right? So according to the Monte Carlo approximation, but okay, average is exactly what we do. 1 over n summation of xi, for example, I goes from 1 to n. This is average. But mean might have another formula for depending on the distribution. How is it calculated? We need to do expectation of x. How do we calculate this expectation of x? Do you remember what was the definition? Summation of x, probability of x. Or if it is continuous, integral of x, probability of x dx. Right? What is probability of x? That's PDF. The formula of PDF. For example, you can use a PDF of Gaussian distribution. If you use this expectation, rather than P of x, put the formula for the PDF of Gaussian. Do you know what that is, right? You know that. And solve this integral, you will end up with the average. Right? Did you understand? So when you calculate expectation, but if you put some other distribution rather than P of x, you will not end up with average. You will end up with another formula. This is called mean of distribution. Okay. For some distributions, mean of distribution becomes average. Okay. So I think it's, rather than saying this, it's better to say it's by Monte Carlo approximation. basically Monte Carlo approximation is assuming that I think the distribution is similar to Gaussian. And I think it makes sense according to the central limit theorem. According to the central limit theorem, when you add up a lot of data points, which are then the distribution of addition becomes like a Gaussian. Okay. By the way, it's not just for Gaussian distribution that the mean becomes average. There are several other distributions, I don't remember which ones exactly, that the mean becomes average. Okay, it's not just for Gaussian distribution. By the way, where were we? Recall the formula of WI in the algorithm. I forgot what we were doing. So we were calculating the probability of error. We ended up in equation 19. So far clear? So far clear? Now recall the formula of WI update of or modification of the weights in the algorithm. It was this, right? J denotes the iteration index here, or in other words, the hierarchy, the model in the hierarchy. Do you agree that I can write this as this? What is the difference of these two? Here, rather than this, I'm writing minus YIHJXI. We already talked about it. Do you remember? We already talked about it in several slides ago, that this indicator function is equivalent to this because YI and HJ are either +1 or -1. Then, so I wrote it as this. And then what happens? It is not harmful to AdaBoost if we use a normalized weights. We normalize the weights. It's not harmful to that. Okay, let's normalize the weights by ZJ. What is ZJ? It's exactly the summation of the numerator over all cases. We have seen it a lot, right? In this case, the weights will be between 0 and 1, and they sum to 1. This is the technique to make some data points to behave like probability. When I have a bunch of the scalars, I want them to behave like a probability. What can I do? I can divide each of them by the summation of all of them. So they become between 0 and 1, and they sum to 1, right? Did you understand? Did you understand everything? Which part were you lost? Tell me, that's fine. No, I will explain again. And then don't be shy, okay? Whenever you are lost somewhere, let me, I will go back and explain again. Okay. So this is our normalized weight, right? For the ith data point and the jth model. And consider, do you remember, initially the weights were 1 over n. Now we can have recursive expression for the weights. Let's see. So this is exactly this. I'm repeating it here. Can I write it as so because WI, how can I explain it? WIKI, consider this and this. WIJ, for that also we have similar formula, where in the numerator I have WIJ minus 1, right? Again, for WIJ minus 1, I have similar formula, where in its numerator I have WIJ minus 2, etc. So multiply this, replace all of these WIs with their formula until you go to WI1. Okay? Then what do you get? In the numerator, you will have the multiplication of ZK until Z1. Also, you will have a lot of multiplications of EXP terms until you have WI1, right? For WI1, you don't replace it with the formula. It's 1 over n. So WI1 is 1 over n. Then this is multiplication. This is also the multiplication. Agreed? What do we do here? Interesting. Multiplication of e's becomes e to the power of summations. In other words, e to the power of a times e to the power of b is e to the power of a plus b, right? So I can write it as this. This multiplication now becomes summation in the exp operator, and I know that yi is not dependent on j in the summation, so I can bring it out of the summation. Agreed? Right? Okay. Then consider this left hand. What did we start with? wik plus 1 equals this, right? Consider this. This is right left hand side. This is right hand side of the equation. Agreed? Multiply the sides by this denominator. So you will get this exact. So far clear? So far clear? Okay. Then, so this is what we found. I'm repeating it here. Let's go. I can't stop it here. Why? Because we are in the middle of the crisis. Okay. What? What? So we just said that this equals this. Agreed? We just proved that. But didn't you understand the proof? So we said that this equals this, right? Forget all of the middle equations. Multiply the sides by this. You will get equation 22. Okay? Let me finish the crisis and then we'll have break. Okay? But I think it's beautiful. It's beautiful. We just found it here. Let's have a flashback to equation 19. Recall equation 19. What was that? I myself forgot it. It's here. It was the probability of error, right? So I'm repeating it here. This is exactly what we had, probability of error. By the way, do you remember what does this mean? Probability of error is less than or equal to this, which we found in equation 19. As a result, this is an upper bound on the probability of error. Agreed? Now I'm simplifying the upper bound using what we just found. What is this? Very interesting. 1 over n times this. Do we have it here? Yes, 1 over n times this. Where is that? Where is that? It's here. Am I right? Am I right? Okay. Replace. So 1 over n is here. These two go away. Replace this with this, right? So basically, we are replacing this with this. It has, 1 over n. Basically, what I'm doing is this. I'm bringing 1 over n inside the summation. Then I'm replacing 1 over n times this with this. Okay? Then what do I have? I have summation of this part times this part. But this part is constant with respect to I. Comes out of the summation. So I will have it here. What remains is this. Is this part. Which is here. Also, this part is repeated here. Interesting. Very interesting. So I'm having it here. And I know that this is upper bound on the probability of error. Now we are simplifying it further. According to equation 20 and 21, do you remember these two? This was equation 20. Let's go back. This is equation 20 that we had. Equation 22 is this. The thing that you asked me and I explained, okay? I'm repeating them here. Sorry, 21, equation 20 and 21. Where is 21? Okay, 20 is this, 21 is this. We had them, okay? I'm repeating them here. So basically that was the normalized weights where Zj is defined here, okay? We know that the summation of the weights becomes 1. Agreed? Okay. Interestingly, here in the upper bound, we had summation of weights, which becomes 1. Right? So the upper bound becomes simplified to this, right? Agreed? Did you get it? What is this? This is notation for therefore in mathematics. On the other hand, okay, let's continue on the other hand after the break. I think it's becoming overwhelming. I don't want it to become overwhelming. So let's pause here, okay, in the middle of the proof, and then we'll continue it after the break. But at the end, what happened? Okay, be careful. Are you fine now? Okay. At the end of this proof, we will find out how beautiful it is, why boosting is working. Okay. Okay. Let's have a break and come back at 8:45. Okay. Okay, great. Okay, so we said we are here. Okay, so where did we stop? Here, right? Here we found this upper bound. We simplified the upper bound on the generalization error of the boosting, AdaBoost. What happened? Okay, we found this, and then on the other hand, equation, yeah, according to equation 21, this was equation 21. You remember? If you don't remember, let me go back for you to remember. That was the denominator of the weights, right? Of the normalized weights. So this was it, equation 21. What do we have? Let's see. This is equation 21. And I can write yi times hjxi as this. Agreed? Indicator function of whether yi equals hjxi, because both are either 1 or -1. And sorry, I can either write it as this or this. So 2 cases might happen. I apologize. If they are equal to each other, then this multiplication is 1. If they are not equal to each other, this multiplication is -1. So this minus goes away in this case. Okay. So I have broken down in this summation into 2 summations. This one and this one. Okay. Now, what happens? This, I bring it out of the summation. This also, I bring it out of the summation. Okay, agreed? Then what happens? So that's, I can bring it because they are not dependent on I. They are not dependent on I. Now, recall equation 20 for Wij plus 1. This was equation 20, the normalized weights, right? Or let me, yes, the normalized weights. So this is in the range between 0 and 1, right? Because of it's normalized. And also its summation over the error cases can be considered as a probability of error, because it's like behaving like a probability. Agreed? So basically, what is this saying? This is kind of can be seen as the probability of error. Agreed? Because this is indicator function of error, misclassification, right? And we know that this WI according to this is between 0 and 1 and they sum to 1. So it behaves like a probability, right? Agreed? And I'm summing over all of the points. So you can see it as a probability of error, right? Do you remember what was LJ? At the start of the slide deck. It was this. LJ was also the probability of error, right? So this is LJ. Agreed? So therefore, equation 24, as a result, this in the equation 24 is LJ, right? Agreed? And what about this one? This one. This is the probability of correct classification, which is 1 minus probability of error. 1 minus LJ. Do you follow me, guys? 1 minus, and the rest is as before. So the exponential operators are as before, here and here, right? Agreed? Now, recall the formula of alpha j in the algorithm. You remember? Right? We can scale it. It's not harmful. So I scale it by 1. I multiply it by half, right? Okay. Therefore, so this is what we found in the previous slide. Now replace alpha j with equation 26. What happens? I will have these, also this, because of these two. Agreed? So we know that 1/2 can be brought as the power of the argument of the logarithm, right? Because logarithm of a to the power of b is b logarithm of a. Agreed? So it becomes second root because of power half. Also, this becomes second root because of power half. Okay. Then, interestingly, these are opposite operations, so they cancel each other. So I will have this plus this. Agreed? So, interestingly, this is 1 minus LJ to the power of half. This is 1 minus LJ. They cancel each other. So it becomes 1 minus LJ to the power of half. Because we bring it inside the square root, right? Also, likewise, LJ to the power of half becomes LJ to the power of half. We bring it in the square root, right? These two, interestingly, are equal to each other. So it will be 2 of them, right? So ZJ was this. We just proved that, okay? Now, we found equations 26, 27, and 23. We put them next to each other. This is alpha j. This is zj. This is the upper bound on the probability of error. Okay? Agreed? Now, let's plug equations 26 and 27, so these two, in equation 23, which is the upper bound on the probability of error. If you substitute them, what happens? So I have alpha j here, replace it with this. I'll get this. Also 1/2, I bring it out of the summation. I have zj, it's here, it's here. Can I bring 2 out of the multiplication? Yes, but I need to power, I have to power it, right? 2 to the power of k, because I have k times multiplication. Agree? In summation, I bring it out, I factor it out. But in multiplication, I need to power it. Agree? Okay. Then what happens? Then I have theta over 2, right? First, I bring it inside the summation. Then I use the formula of logarithm of b logarithm of a equals logarithm of a to the power of b. So I bring it as a power, like here. 2 to the power of k is, I bring it here, outside. I just changes the order of multiplication. I bring it here. So the rest is as before, okay? We know that e to the power of a plus e to the power of b equals e to the power of a times b, right? So this summation becomes, so exp of summations becomes multiplication of exp. Agreed? Do you follow? Right? Then the rest is as before. Interestingly, exp and logarithm are opposite operators. They cancel each other. So it simplifies to this, right? And this is as before. The rest is as before. Agreed? I have 2 multiplications over j, so I can merge them into one multiplication, because multiplication of multiplications is multiplication, right? And one of them has square root, one of them has the power theta over 2. So this has power of theta over 2, this has power of half. So as a result, I can bring both of them in under the square root, right? Where this one has theta in. Agreed? As you see, for understanding these lectures, you just need to know calculus, right? The simple how to do work with the square root, logarithm, and uses. Okay. Then, interestingly, I have Lj here. No, I have Lj to the power of theta. Also Lj here. Simplify them, it becomes Lj to the power of 1 minus theta. Here, I have 1 minus Lj to the power of theta, also 1 minus Lj. So I will have 1 minus Lj to the power of 1 plus theta. Agreed? We just simplified the upper bound. We are simplifying the upper bound for half an hour, right? Okay. Okay. So this is what we found. So this is exactly what we found. We found the upper bound on the generalization error of AdaBoost. Okay. This is the probability of the generalization error or true error for the ith instance, right? To be less than theta. Okay. Now, do remember Lj was this, equation 3, the definition of the loss of the Jth model. Lj as a result is between 0 and 1. Do you agree? Do you agree? Because it's normalized. C is numerator, denominator, right? So what if we have this? What is this? Can you tell me? Equation 29. I'm waiting for your answer. What is equation 29? It means that Lj, the probability of error, is slightly less than half. What does it mean? My accuracy is what? No. Lj should be minimized. Lj equals 0 is the best. Lj equals half or greater than half is awful. Lj equals half is coin, random coin, right? Lj is minus half minus epsilon is slightly better than coin, right? Because when the probability of error is half minus epsilon is slightly better than, its accuracy is slightly greater than 50%, slightly, right? When the error is slightly less than 50%, the accuracy is slightly greater than 50%, right? Therefore, it's this side, right-hand side, is slightly better than coin. Lj less than this, it means that either slightly better than coin or much better. Okay? If this happens, assume zeta here is between 0 and half. Okay? Then what happens? So basically, this condition means that it's at least better than random classification. Okay. What happens? Let's see. Let's put it in the upper bound and see what happens. I just want to prove to you why I said if we have slight weak classifiers and boost them, it becomes a monster. Let's see. So this is probability of error. We have 2 to the power of k. We have this. This is what I'm repeating. Now I bring 2 to the power of k inside the multiplication, so it becomes 2. Right? I bring 2 inside the square root, so it becomes 2 to the power of 2. Then can I write 2 to the power of 2 as 2 to the power of 1 minus theta times 2 to the power of 1 plus theta? Agree. As a result, I can, these two have the same power. I merge them. These two have the same power or merge them. Agreed? Then let me think. Let me think. One minus. So yes, exactly. Consider equation 29. What is L? So multiply the sides of equation 29 by 2. 2Lj becomes less than or equal to 1 minus zeta. 1 minus 2 zeta, sorry. 1 minus 2 zeta to the power of 1 minus theta, right? Agreed? Now, equation 29, consider 2 times 1 minus Lj. Let me write it down. So what is 1 minus Lj? It becomes greater than or equal to, am I right? No. Yes. So 1 minus Lj. 1 minus Lj becomes what? Can you tell me? Sorry, minus Lj. It becomes greater than or equal to minus half plus zeta. 1 minus Lj becomes greater than or equal to minus 1 plus 2. Sorry, 1. 1 minus half becomes half plus zeta. Agreed? 2 times 1 minus Lj becomes greater than 1 plus 2 zeta. Here. Agreed? I'm confused about one point, that here this we have greater than or equal to. Can you help me? What? Which one? Second bullet point, okay?
We can start from here.
Okay. No, I understood until this point. Did you understand too? The reason that, okay, why is it less than or equal to? Because we know that 2Lj is less than or equal to 1 minus 2 zeta, and the power is the same, right? But the issue is 2 times 1 minus Lj. Minus Lj, let me think. Minus Lj is greater than or equal to minus half plus zeta. 1 minus Lj. Is it? What?
Is the value the right side only. So that's why the
I didn't understand.
Just there is two portion on the equation. So the right side they have
This right.
but this side they didn't. That's why it's less than equal.
No, I'm saying that I understand that this part is less than this part. What about this part? It's greater than this part, right? I myself never thought of this before. I just found this. I don't know what has happened here. Okay, anyway. Assuming that this is true, sorry about it, I don't know why this is happening, but if you can find out, please let me know. Maybe I'm tired. Am I making a mistake? Now I'm doubting myself, my understanding. I think maybe there's something that I'm missing right now. Anyway. Okay, assuming that that was correct. So again, this is under discussion. Okay. Then we have this. Did you get it? We have this. We simplified the upper bound and the probability of error. Okay. This is a very good upper bound. Can you tell me why? Because what was theta? Do you remember? If theta was 0, we had absolute misclassification. If it is less, the probability of error, the y, I mean this. If this is less than or equal to 0, it's absolute misclassification. We relaxed that a little bit. We said theta is a small positive number, right? Then if theta is less than zeta, what happens? This becomes less than 1. Okay, thus the probability of the error, if, by the way, if you don't know why this is happening, just try to plot this function and you will see that this is true. When theta is less than zeta, this function becomes less than 1. Okay, then the probability of error, which was this, the probability of error decreases exponentially with k, which is the number of models used in boosting. Because of this. Do you know why? Because inside this to the power of k, right? This to the power of k. Then when inside the power I have less than 1 values, what happens? 0.9 times 0.8 times 0.9 times 0.7 times 0.6, etc. They become too small. And they become small exponentially. And they become smaller when k is a large number, when I have a large hierarchy. Agreed? So the larger, the better. Okay, because my boosting becomes stronger. This shows that boosting helps us reduce the generalization error, right? And helps us avoid overfitting. Okay? Did you understand? You know, I haven't yet explained why for the weak classifier, but I'm explaining why boosting now is very good. Why is this generalization error is very good? Okay, because when we do that, we just showed that we have a little smaller than 1 values to the power of k, and if for the large k it becomes too small, probability of error. Okay, in other words, because of the bound and generalization error, boosting overfits very hardly. So one of the techniques not to have overfitting is using boosting. Okay, if zeta is a very small positive number, then Lj, do you remember Lj was less than or equal to half minus zeta? Do you remember that? Is a little smaller than half when zeta is a small positive number. That is, Lj is close, slightly less than half. Agreed? When Lj is slightly less than half, what does it mean? I'm slightly better. My accuracy is slightly better than 50%, right? So I'm slightly better than random classification, right? Then what happens? Therefore, for having a great bound on equation 30, having weak base models a little better than random noise suffices. Let's see what. We know Lj equals half means random classification by flipping a coin. Therefore, for having a great bound for equation 30, which was this, I'm repeating it here. Okay. What happens? Let me explain this again. Let me explain this. I said, when do you agree that if zeta is a small positive number, such as 0.0001, okay, Then, according to this equation 29, I'm a weak classifier. I'm a slightly better than random classification. Agree? Now put a small zeta number in this equation, in this upper bound. What happens? Almost this becomes a very small. So 1 minus 2 zeta is less than 1 to the power of something. Again, 1 plus 2 zeta to the power of the whole thing. According to what I explained here, this whole thing, which is to the power of k, is less than 1. As a result, it becomes too small. Okay. Therefore, when zeta is small, this Lj is a little smaller than half. But according to this upper bound, the probability of error becomes too small because of the power smaller than 1 to the power of k. Okay, it's become too small. If I have, for example, accuracy 51, accuracy 52, accuracy 53, because of this power of k, the whole thing accuracies blows up, exponential. Did you understand it? Did you understand? Okay. A very small zeta means that a very small theta. Okay, it explains a bit better. What I said explains it a bit better. Note that a very small zeta means a very small theta, according to this. Right? Right? Because theta is less than zeta. Therefore, it means that a very small probability of error because of this. Right? It is noteworthy that both boosting and bagging can be seen as ensemble learning or model average. Okay. Moreover, both boosting and bagging reduce the variance of estimation. Okay. For the models with high variance of estimation, so it's a good technique to use boosting for reducing the variance of estimation. Okay. And we analyze it for binary classification. You might say, why are we using it for binary classification? We might have multi-class classification. Similar analysis exists for multi-class classification. Okay, we can extend it to multi-class classification for generalization error. You can see appendix in the reference 9 for more details. So far, I explained the proofs of the AdaBoost and the probability of error. Okay. Now, another thing, we can see boosting as a maximum margin classifier. Where did we see maximum margin classifier? We saw it in SVM. Interestingly, we can analyze boosting as an SVM. Let's see. In another perspective, the found upper bound for boosting shows that boosting can be seen as a method to increase or maximize the margins of training error, which results in a good generalization error. Do you remember SVM had a good generalization error because it was maximizing the margin between the classes, right? And the decision boundary. This phenomenon is the theory of support vector machines, right? Now here we analyze the analogy between maximum margin classifier, which is SVM, and boosting, according to reference 9. In addition to 9, some more discussions exist for upper bound and marginal boosting. Okay, you can see these references. Now assume we have a training data set and training data points x1 to xn and their labels y1 to yn, where yi is -1 or 1 for classification. Agreed? Okay. Again, for SVM, we were having binary classification. In boosting, we are assuming for now it's binary classifier, right? Okay. Then the two classes may not be linearly separable, right? In order to handle this case, we map the data to higher dimensional feature space using kernels. Do you remember kernel SVM? Hoping that they become linearly separable in the feature space. Agree? Okay. Now assume h of x is a vector which non-linearly maps data to the feature space. H of x, which is the model, right? maps it. So basically, assume h of x here is the pooling function. Brings that to the feature space. Okay. Now consider alpha as a vector of optimization variables. So my optimization variables are alpha. This is the optimization problem in SVM. Do you remember this? Do you know why? Do you remember when we were proving SVM? We had this. I think there we had, rather than alpha, we denoted that by beta. Do you remember this? The proof of SVM. If you don't remember, go to the our SVM lecture. We had this similar to this. And here, what is this maximum minimize? I talked about it. Do you remember? I said when we have a primal optimization variable, we want to minimize this cost function. It's equivalent to maximizing a dual optimization function, right? And I said there might be a gap between them. If it is a gap, a positive gap, it is weak duality. If there is a zero gap, it's strong duality. Do you remember? So here, my alpha are the dual optimization variables, and xi and yi's are the primal optimization variables. Okay. Yi is +1 or -1, and alpha transpose hxi is either greater than 0 or less than 0. Okay, because here, and as a result, the sign of yi and this determines the class of the ith instance. So here we just reviewed SVM. Okay, now let's see how it is related to our thing. This is what we had. On the other hand, according to equation 16 in AdaBoost, this is what we have. Okay, do you remember? This is the aggregated predictions by the models, right? Which is normalized also. Can we write it in vector form? The numerator, what is that? The inner product between vector alpha and h. Agreed? What is the denominator? L1 norm of alpha. Agreed? Agreed? Now, can you compare these two? What is the difference? What is the difference? Label? No, the formulas, I mean. This and... No, this is L2 norm, this is L1 norm. So basically in SVM, we have L2 norm. But in boosting, apparently we are having L1 norm, okay? So here also, hxi is +1 or -1. So here, the bold h is a vector of h. So the models, right? The K models. And also every alpha here in AdaBoost is this, the formula of alpha in the algorithm, right? Now it shows that the boosting can be seen as maximizing the margin of the classification as in SVM, resulting in good generalization error, but we are using L1 norm. Now we know that SVM maximizes the margin. We just showed that boosting also maximizes the margin, but with another norm, right? And we know that when we maximize the margin, what happened? The generalization error is decreased, minimized. Do you remember? Vapnik tried to find the best decision boundary. He said, perceptron finds anything. Let's find the best one to have the least amount of generalization error. Here we just showed that it has the least amount of generalization error as well. In other words, finding a linear combination in the high dimensional feature space having a large margin between the training instances of the classes is performed in both of the methods. Okay, the type of norm, as I said, here we are using L1 norm in boosting, but in SVM it is L2 norm. Another connection between SVM, which is maximum margin classifier, and boosting is that some of the training instances are found to be most important instances called support vectors. Do you see that? Do you see the analogy here between SVM and boosting? in addition to the maximizing the margin. What did we have? Why do we call support vector machine support vector machine? Because of support vectors, right? The support vectors were the points close points of the classes closest to the decision boundary. In other words, they are more capable of being confused with the other class, right? Do you remember that? So some of the points were more important, right? On the other hand, in boosting, what did we say? We experiment the model, trained model on the points, and we see some of them, for some of the points, this model is performing poorly. So we weight them more. In other words, we say some of the points are more important. Let's weight them more. Do you see? Kind of, we are having support vectors like support vectors in boosting as well. We are weighting them. Right? Interesting. In boosting, weighting the instances can be seen as selecting some informative models, which can be analogous to support vectors. Okay. Acknowledgement for more information on boosting, you can see the book of Hasty and Tipshirani at Stanford, The Elements of Statistical Learning. Some slides are based on our tutorial paper. I suggest that you read this tutorial paper. I think this is a very informative paper. The theory behind overfitting, cross-validation, regularization, bagging, and boosting tutorial. So it talks about overfitting, cross-validation, regularization, bagging, and boosting, all of it. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo and Professor Huda Mohammed-Zadeh at Sharif University. These are the references. Any question before we move to the next thing? No? Just before we go to the next thing, can I think about one thing? Because when I don't explain something very well, I understand it. You can also tell me, I didn't explain this slide very well. Let me think. I need to think. Okay. Yes. When zeta is a small number. Oh. Okay. Okay. Let me re-explain this slide because I was not happy with that. Was my explanation. Okay. So at least two important things, in addition to these additional explanations, which are easy, two important notes were explained in this slide. Let me explain them again. One thing, analysis of this. Why? So two things. One, why this upper bound on the generalization error is good. So why boosting is working well. The second note was why, if we have a lot of weak classifiers, they become very good. The whole thing becomes very good. Okay. So the first one, why is this generalization error good? What happens? Let's analyze this formula. This is upper bound on the generalization error, right? By the way, by this, I haven't written it completely. Sorry, I meant this. Okay? Okay. Okay. So, let's analyze it. Do you remember the probability of error is this, right? Probability of yi times f hat, which is the estimated label, is less than or equal to theta. Agreed? And I said, assume now theta is less than some zeta. Okay. If we plot You can plot it by computer, whatever. The function square root of this big function, you will understand that if theta is less than zeta in those regions, this function is less than 1. Okay? Okay. Then I will have this less than 1 to the power of k. And where did this power k come from? Because here I had multiplications for k times, and each of them were less than this. In other words, the whole thing is less than this to the power of k. Okay. Then I said this inside the power is less than 1. I have a lot of less than 1s which are to the power of k. Okay, assume it's 0.9, then 0.9 to the power of k. What happens? And k, when it's, for example, 0.9 to the power of 10, it becomes very small. Exponentially becomes very small. You know, this shows that why the probability of error in boosting is very low. Why the boosting is working very well. Why accuracy in boosting is high. Agree? So this was the first point in this slide. The second point now, which I didn't explain very well, is that now consider the models are slightly weak, slightly better than random classification. So they are all weak. Okay. What does it mean? According to this, do you remember this was the formula that we had in the previous slides? Lj is less than or equal to half minus zeta. Okay. Then when I say slightly better than random classification, here it's binary classification, it basically means Lj is less than or equal to, you tell me. It's close to half, but it's less than half. If it is greater than half, it's awful, even worse than random classification. So here, if zeta is a small positive number, then my Jth model is a little bit better than random classification. Okay. Now let's see what happens if zeta is a small. If zeta is a small, according to this, which I'm drawing over, I know that zeta, if I analyze this in this region, right? I said in this region, this is which is in the power is less than 1. Agree? So according to this, zeta is an upper bound on theta. Right? Right? What was theta? Here in the probability of error. I know that when zeta is small, theta must be also to be small. So the probability of error, this becomes too small. Because this zeta is small, theta is small also. So the whole thing becomes, how should I say? Yeah. Because the whole, I know its explanation is a bit hard for me to transfer it here. But when zeta is small, theta must be small. And theta here, if you remember, we relaxed it. It was 0. It was 0 for completely misclassification. So zeta must be small, right? But we never said it's a small unless zeta, which is its upper bound, is a small. In this case, this is very low. And according to our first point, I have a slightly very weak, times very weak, times very weak, times very weak. But each of them, they have some probability of error, but I have k of them. The whole thing becomes small. In other words, I think by some example, it is understandable better. When I say I have weak classifiers, their errors become their errors, for example, becomes 0.9, right? 0.9, I think, is awful. Their errors become, you tell me, 0.4, 0.49, right? Let me add a page. 0.49. Guys, please listen to me. 0.49, the error, right? Awful, a bit better than, because 0.5 is random, right? 0.49 k times. What happens to the probability of error for the whole thing? Very small, right? This is the reason. I think by this example, I could explain it better. Okay? Okay. Let's go to the next topic. Sorry that I couldn't explain this part very well. I tried my best. Okay. Okay. So the other part is mixture models. We can't finish it, but we'll go on until where we can, and then we'll continue in the next session. Mixture distribution. First, let's talk about point estimation. So assume we have a sample with size n, so x1 to xn, okay? And also assume that we know that the distribution from which this sample has been randomly drawn, so we know the distribution, right? But we do not know the parameters of this distribution. So we know what, for example, we know that they are sampled from Gaussian distribution, but we don't know the mean and covariance. Agreed? Okay. For example, yeah, as I said, from the normal distribution, but we don't know but the mean and variance are unknown. The goal here is to estimate the parameters of the distribution using the sample. So I have some sample, right? But I know they have Gaussian distribution, but I don't know the mean and the covariance. Let's estimate the mean and covariance using the sample, right? This is called point estimation in the statistics. Okay. Then this estimation of parameters from the available sample is called point estimation. One of the methods for doing that is called maximum likelihood estimation. The other one is called, you tell me. I bet you have heard of it. Maximum a posteriori. Have you heard of it? A posteriori, right? Recall Bayes rule. This is Bayes rule, right? This is Bayes rule. This is called likelihood. Do you remember? This is called posterior. This is called prior of theta, and this is called prior of x, right? Maximum likelihood estimation maximizes the likelihood according to its name. Maximum a posteriori, what does it do? Maximizes the posterior. Okay. By the way, when we say maximum likelihood estimation, when I say maximum in the likelihood with respect to what? The parameters of the distribution, right? So which parameters of the distribution maximizes the likelihood of data? The maximum a posteriori says which parameters of the distribution maximizes the posterior. Okay. Can you tell me what is the difference between maximum likelihood estimation and maximum a priori? In short, MLE and MAP. Can you tell me? So assume I'm maximizing the likelihood or maximizing the posterior. What is the difference between them? Posterior is likelihood times prior, right? Some over another prior. This prior in the denominator is the same for everyone, right? It doesn't depend on theta. Drop it. Okay. So maximum likelihood only maximizes the likelihood with respect to theta. Maximum posteriori maximizes F posterior with respect to theta. What is posterior? It's likelihood times prior of theta. So whenever prior of theta is important to me, I do maximum posterior. But whenever I don't care about the prior, I do maximum likelihood estimation. Forget theta. Assume theta is class, okay? Not the parameters of the distribution. Then posterior, we use posterior if the prior of the class is important to me. When is the prior of the class important to me? How do we estimate prior of classes in machine learning? In LDA lecture we saw that. How do we estimate the prior of the class? We estimate it by cardinality of the class over the whole sample size, the whole number of data points. Agreed? Next week we have exam, guys. Yeah, exactly. Don't memorize it. Don't memorize. But you should know where it was, right? So this is how we estimate it. When is this estimation important? When the cardinality of the classes is the same, the estimation is not important. The prior of the class is not important. When the cardinalities of the classes are very different, the prior becomes important. In other words, when the classes are imbalanced. So when the classes are imbalanced, the priors will change, and then posterior becomes important. But when the classes are balanced almost, likelihood is important only. Priors are not. Agreed? Okay. So let's going back to maximum likelihood estimation. We maximize the likelihood. So we postulate that the values of the sample, which are x1 to xn, are independent random variables, and they have the same distribution. So they are IID, or independent and identically distributed. Okay. So xi has some probability fx, right? With the same parameter. That's why we call it identically distributed. Same parameter. And this is Bayes' rule. Agree? Okay. Then maximum likelihood estimation, or MLE, what does it do? Maximizes the likelihood with respect to theta. Argmax of this maximization is called theta hat, the estimated parameter. Estimated. By the way, you know that every distribution might have different number of parameters, right? For example, Gaussian has 2 parameters, mean and covariance, right? Another distribution might have 1 parameter or 3 parameters, depending on the distribution. So as the points are IID, the likelihood can be written as this. This was the likelihood, right? This was the likelihood. So we can, by the way, there are several ways to write the likelihood. Sometimes they use this line. Sometimes they use this. What does semicolon mean? It means that these are the parameters. Okay. So either either in this case, in this notation, people are saying that I assume my parameters are random variables conditioned on them. In this notation, they say they don't necessarily see the parameters as random variables. They say these are the parameters of the distribution. Okay. Anyway, doesn't matter. This is just notation. Then I can write them as multiplication of this, because they are IID, right? The likelihood of the whole thing, you can write it as multiplication of all the likelihoods. Agreed? Agreed? Okay. Now, yeah, this in the literature we can write this as L theta. Not my notation, okay? L of x1 to xn given theta, let's assume denoted by L theta for simplicity. Agreed? Okay. Usually, for more convenience, we use log likelihood rather than likelihood. Can you tell me 2 reasons at least? Yes, 2 reasons for why we use log likelihood rather than likelihood, or log posterior rather than posterior in machine learning. At least 2 reasons.
No, helps in like creating the levels, like we have minus infinity, we change that minus 1.
Log is not restricted to -1. So this is log, right? Log it's also between minus infinity and infinity. Log is not restricted to a range. It goes to minus infinity to infinity. You?
It's big,
Yes, kind of answered the question. It reduces the complexity, but how? In two ways. Logarithm doesn't change.
Compared to other functions, like an exponential function, I think logarithm has a more global behavior and maybe.
Maybe, but maybe. But usually we use logarithm the other way around that you said. You said logarithm dampens the oscillations. I said that the logarithm exaggerates the oscillations. Have you worked with the loss functions of neural networks? For example, when you show them, it's like going like this. You don't see the oscillations a lot. You plot the logarithm of the loss, then you'll see a lot of oscillations. It exaggerates the oscillations. You see what I'm saying? So let me give you a hint. Many of the distributions have exponential operator in them, right? Such as Gaussian distribution. So they are called exponential family of distributions, right? EXP, exponential operator, is a pain in the neck. What should we do? For removing them, we should use its opposite operator, which is logarithm. So one of them is get rid of EXP. The second reason is what? Why we use likelihood. There is another thing which is pain in the neck. There's another thing which is pain in the neck. You can see it here even. Multiplication is a pain in the neck. Which one is easier to work with, multiplication or summation? Summation. So in order to convert multiplication to summation, we use logarithm. Can you tell me why do we see multiplication a lot in machine learning? Here in probability. Let me give you a hint. I gave you a hint. IID. What does it tell you? The distributions are independent and identically distributed. So I can write their probabilities as a multiplication of the probabilities. So we see multiplication probability area of machine learning a lot, right? And this multiplication is a pain in the neck. And I know that probabilities have a lot of exponential operators. So I've killed two birds with the same stone. I use logarithm. Interesting. So logarithm of likelihood, they usually denote likelihood with capital L and likelihood with a small l. Convention. Okay. Logarithm of multiplication of f's becomes summation of logarithm of f's. Agreed? Logarithm of a times b becomes logarithm of a plus logarithm of b. Then, so argmax of log likelihood rather than l. It gives me theta hat. Okay. Another one was maximum a posteriori, as I said. I maximize the posterior. Expectation maximization. I think this conversation is interesting. So sometimes the data are not fully observable. Okay. I will tell you some examples. For example, the data are known to be whether 0 or greater than 0. Greater than 0 is vague. Is it 1? Is it 1,000? What? Right? As an illustration, some example. Assume the data are collected for a particular disease, but for convenience of the patients participated in the survey, the severity of the disease is not recorded, but only the existence or non-existence of the disease is reported. So the data are not giving complete information. Either it is greater than 0 or 0. In this case, maximum can I use maximum likelihood estimation in this case? No, because I don't know everything. Okay. For maximum likelihood estimation, everything should be crystal clear. So in this case, I use something named expectation maximization. In this case, MLE can not be used because we do not have access to complete information and some data are missing. Now, please focus and listen to this conversation. It's like a movie. Listen. Consider two people talking. The main idea of EM is this. What shall we do? The data is missing. What should we do? The log likelihood is not known completely, right? When some data is not known completely, the log likelihood is also not known completely. So MLE cannot be used, maximum likelihood estimation. Probably we can replace the missing data with something. Replace the missing data with something. But what do we replace it with? Let us replace it with its mean. Right? The first one which comes to mind is mean or expectation. Mean is another name for expectation. You're right. We can take the mean of the log likelihood over the possible values of the missing data. The missing data can take some possible values, right? Then everything in the log likelihood will be known. And then suddenly the other person jumps in the conversation, says, and then we can do MLE. Do you see the beauty? So now do you understand? Do you get it why it's called expectation maximization? It has two stages, right? First, we replace the missing data with the expected value. Then it is suitable, it's ready to do maximum likelihood estimation when we maximize it. So we have log likelihood, we get its expectation, then we maximize it for the sake of MLE. Okay? So in other words, expectation maximization has MLE inside with some pre-process expectation, right? And by the way, it's done iteratively. Expectation maximization. Again, expectation maximization. Okay. So let me explain this slide and we finish. So assume the OBS is the observed data and D miss is the missing data. For example, XI 0 in the 0. Do you remember the example of XI is either 0 or greater than 0? 0 is observed data and greater than 0 is the missing data. Okay. The EM algorithm or expectation maximization includes two main steps, E step or M step. E step, expectation step, M step, maximization step. In the E step, the log likelihood equation 4 is taken expectation with respect to the missing data in order to have a mean estimation of it. Okay. So let's define it, denoted by Q theta. Q theta is the expectation of log likelihood with respect to C, the missing data, missing data, given, so it's a conditional expectation. Recall preliminaries for conditional expectation. Expectation of log likelihood with respect to missing data given observed data and theta, the parameters, right? Given everything else. And in the M step, maximization step, then everything is ready for maximizing the log likelihood, the Q of theta. Q of theta is expectation of log likelihood, right? These two steps are done iteratively, repeated iteratively until convergence of the estimated parameters. One iteration is not enough. Why? Because who says that expectation is a good thing? Because you expect things, then you maximize things, but by this maximization, what you find, the expectation might change. You need to do it iteratively. Similar to the idea of alternating optimization, or so an alternative optimization, you optimize over a variable, then optimize over another variable, but when you do that, your first solution might not be valid anymore. You do it iteratively until they converge. Okay. in the next session, at the start of the next session, we will talk about mixture distribution. And a good example of using expectation maximization is in mixture distribution, such as Gaussian mixture distribution. And mixture distribution basically means that let's have a linear combination of several distributions. Rather than one mode, let's have several modes of distribution. Okay. Any question? No. Duration of the test? I think it will be 3 hours. No, I mean, I give you a lot of time. So I'm giving you enough time to do the task completely and with peace of mind. Okay. And I will be there to answer your questions. And by the way, I will let you know also in the announcement, but bring phones and install camera scanner to take pictures of your answers and make them PDF and upload it. Okay. I should see how many there were, but is it important how many questions? Let me see. I don't remember.